After choosing PIC 24 for our course, the Embedded System Design, also after introducing the language that we are going to use to program our microcontroller, which is C, today we will discuss the first module, which is very critical and important to understand. It's the general purpose I/O. And we will explain this along a very simple example. So for this time, we will talk about LEDs. Also, we'll talk about switches, and we will go through all the big 24 pins. And especially, we will focus and today on the subject of the GPIO. Before we go there, it's important to remind you that you need to be able to read data sheets. The data sheets and also the family reference manuals or the FRM contain all the information that you need. Of course, based on your choice of microcontroller, their data sheet will give you different specification and control registers. So you must be able to read it, go through the section, understand which one discuss, and then also the big 24 family reference manual has a different section for each major subsystem. Basically, usually they talk about the CPU first, and then they go through the modules one by one. So this is our big 24. It's called big 24 HG32GB202 microcontroller. If you go to its data sheet on page 13, you will see the bin diagram. You can see that it contains 28 pins, starting from 1, 2, all the way to 14, and then you go to the other side, 15, all the way to 28. If you hold the chip on your hand, or it's in front of you, look for this mark to know that this is the starting pin, or this mark. On the left will be the first pin. Also, from the looks of it, you can see that many of these pins, they are shared. They have shared functionality. We will go through them one by one, but first, just to clarify everything, we separate them out a little bit for the easy of explaining each part in the coming few slides. So first, you can see that we have the VSS, VDD, AVDD, AVSS, and the VCAP, VDD core, and the VSS. The VDD and the VSS, this is the bar and the ground voltage sources. And usually this, or the VDD and the VSS is for the digital voltage. For the AVDD and the AVSS, this is for the analog. The VCAP and the VDD core, this is the internal voltage. The big 24, as we will see many times throughout the class, runs at 3.3 volt. So the VDD will be 3.3 volt, and the VSS, of course, it's the ground, which is 0 volt. Next, we have the master clear. This is for reset purpose, and you can see that it is active low. Also, we have the BGED 1 and 2, and also 3. We have the BGEC 1, 2, and also 3. So they are used for the in-circuit serial programming, one for the clock and one for the data. The C is for the clock and the D is for the data. So when you need to program the big 24, you need to work with these, with one of the three choices, either 1 or 2 or 3. Next, we have the different oscillators and clock sources. Later, we will talk about the oscillator in a class by itself, but it's good to know that if you choose an external source, you can use the oscillator input and oscillator output, or the secondary oscillator input and the secondary oscillator output if you choose a crystal. If you choose a crystal, as you can see. We will explain this further by the time when we reach to the oscillator class or lecture. We have the clock input and the clock output. This is only you use them if you have a clock, you know, it's low and high and low and high and so on. That was generated from an outsource. And you want to feed it through the PIC24. So if it is not a crystal, you would use the clock input to feed it in the system. And if you want to give it to another chip or another PIC24 or any other microcontroller, you can use the clock output. We have also here the GPIO, which is what we will discuss in details in this talk. As you can see here, we have two boards, A, the blue one, and B, the black ones. So you can see that the first board is A, have 5 bits, 0, 1, 2, 3, and 4, while B have 16 bits, starting from 0 all the way to 15. So it's 16 bits. It is called parallel board input output. And these are the boards that are available in the PIC24. And they are the GPIOs, meaning that we can choose and program one of them to be input or output. Next, we have the change notification inputs. It starts from change notification 0 all the way. You can see here that the maximum one is change notification 30. And if you go through them, you will see that some of them are missing, which is fine. It depends on the microcontroller. Some of them is not there. You can see also that they are usually tied to boards, either A or B, and so on. Also, we will talk about the change notification in detail, and one of its important job, we'll talk about it this time, and then other job, we'll talk about it when we talk about the interrupt. We have the RPs. They are from 0 all the way to 15, so that we have 16 of them. These are remappable peripheral pins that allow internal pins function to be connected in a flexible manner. Usually, we use these RPs when we want to input or output an information and it doesn't have a specific pin. If it doesn't have a specific pin, these are the choices that you can choose from. Also, we will talk about this later when we talk about one of the module, which is the interrupt. Here we have the AN0 all the way to AN12. You can see that we have 0, 1, 2, 3, 4, and 5. 6, 7, and 8 are not there. And then 9, 10, 11, and 12. This is for the analog inputs. So some of the pins, you can make them digital or analog based on your preference. We will revisit those and we will see how to deal with them when we talk about the analog to digital converter modules. We also here have the V reference, plus and minus. Also, this is the reference voltage when you convert from analog to digital. So we actually need to specify them. Usually we make the V reference plus some voltage, maybe 5, maybe 3.3 volt, maybe more or less. But the V reference minus, usually we make it 0. Next, we have the T1 clock. This is timer 1 external clock input. We can use an internal clock source or an external. If you choose the external one, then you have it here for timer 1. We also have the ASCL1 and ASDA1, also the SCL1 and the SDA1, and these pin pairs implement the I to C synchronous serial data interface that is used for communication. So one of them will be for the data, one of them will be for the clock, and so on. Next, we have N0, and this is an external interrupt pin, and we use notification, or we denote it with 0. We have N0. We have other interrupt types, and we will also revisit this when we talk about the interrupt. We have here 4 pins: the TMS, the T clock, the test data input, and the data output. This is for testing. If you want to test the BIC24, or you do some design for testability, you can make use of these pins. You can use the test mode, whether it's normal or test mode. You can choose the test clock, and then you have the data input and the data output in these 2 pins. So what we did is we kind of look at all the pins. We see some of the functionality. We just named them. We didn't describe much. Today, we will focus on port A and port B, and how to program them or identify them to make them input or outputs. So let's start by explaining the switch. We need to understand the switch because it will be one of the easiest inputs. It's just a switch. We can make it on or off using a push button, or you click it using this type of switch. So a switch will be closed and conduct current, meaning it's turned on when it is pushed, or it will be off when it is released, if it is a push button. So let's see here for this specific connection. If the switch is in the release, it's not push, it's in the release state. You have VDD going through the transistor, and it's fed to this line. If you click the switch, these 2 boards will be connected, and the VDD will go through the resistance to the ground. So the ground will be connected to this line. So if in the current state, this will be 1. If it is pushed, it will feed to 0. You can make the connection the way you like, whatever you like. We make this line 1 or 0, and we will see this soon. We have, as I said, many types of switches. These are some of the types. What about the lid? The lid usually is connected to the output. So here we have usually an anode, which is the long lead. If you can see here, if you take one of the examples or the very common lids like this one. So the long one will be the anode, and the short one will be the cathode. And if you apply 3.3 volt here and you have a resistance, this resistance 470 ohm, then you can count or you can calculate the running current. Be aware of using always a resistance in series with the LED, otherwise it will burn. So make sure you always use an appropriate resistance. For this one, a diode will conduct the current or turned on when the anode is at approximately 0.7 volts, higher than the cathode. The light emitting diode or the LED emits visible light when conducting, and the brightness is proportional to the running current through the LED. Now, the voltage drop across the LED used in the lab is about 2 volts. So it's about 2 volts across the LED. And you can calculate the current using ohm law. The current will be voltage divided by the resistance. So it will be 3.3 volts minus the voltage drop across the LED divided by 470 in this example. And it will be about 2.7 milliampere. Be aware that for each LED, it has a maximum current that it could work with. For this, the common LEDs, usually it's about 4 milliampere. So be careful when you work with the LEDs, always connect them with appropriate resistance. Now, if we have a big 24 and we want to work with it to do any application, there is a recommended minimum connection that you need to do before working with any system that you want to use a microcontroller for. So as you can see here, we have the master clear. It's an active low connected with the push button this way. So this is very close to the one that we just discussed. So if the push button in the release state, we will have logic 1 feed it to the master clear, which means that the system will not be resetted. So it will work in the normal way. If you press the reset button here, the ground will be connected to this part, and you can reset the PIC24. You can see that we use the resistance to limit the currents. That's the important part here. We want to limit the currents. We want to limit the current between the VDD and the ground when you connect the reset or when you push the reset button. Otherwise, you'll have a short between the VDD and the ground. Also, we have a resistance here. So you make sure that the internal connectivity here inside the PIC24 also protected by this resistance. In case you have a spiked voltage, this capacitor will suck in this high spikes. Also, the VDD and the VSS, the VSS and the AVSS, they are connected to the ground. The AVDD and the VDD will be connected to the voltage that is appropriate to the microcontroller. And for our case, it will be 3.3 volts. Between the VDD and the ground, it's recommended also to use a ceramic capacitance. 0.1 microfarad is enough. And just to protect the voltage sources, it's better to connect the VDD and the AVDD with a series resistance. It doesn't have to be big. 10 ohm is enough. That's the minimum recommended connection. Now, next we will move to the switch options and also the LED options. So here in the switch, we can connect it as a pull-up resistor. The switch obviously will be connected to an input to the PIC24. You want to input a value. If you choose a pull-up resistor, you can see that the resistor connected to the VDD, so it's pulling it up. At this point, if the switch in the release state, you will have 1 in the input because it's connected to the VDD, so you will have a logic 1. If it is pushed, at this point, the VDD will be connected to the ground, and this will make the charge here disappear, meaning that the voltage here will be, or the value here will be logic 0. If you choose the other setup, actually, we switched this, we exchanged the places between the switch and the transistor. So now the transistor is pulling down. At this point, if you didn't, or the switch in the release state, the input here is logic 0. If you push the button, then you will have it as logic 1 or the VDD. So this is the two options that you have for a switch. For the lid, similarly, but we call them current source or current sink. If it's a current source, obviously the lids are connected to outputs. So if the lids is connected to a current source, now if you have a voltage difference between this point and this point, then the lid will emit light. If there is no voltage difference, then the lid will be off. So at this point, if you have logic 1 here, since you are connected to a ground here, there will be voltage difference and the lid will be emitting light. If it is logic 1. If it is 0, it's not going to be on. For this one, if you choose a current sink, if the output is logic 1, the lid will be off. If the output is logic 0, then the lid will be on because you will have a voltage difference. Now, which one to choose for the switch and for the lid? The best choices for the switch, you can actually choose. Sometimes you choose this setup or this setup. It depends on what you want to feed. Do you want the input to be active low or active high? So when we want active low, like the reset, we choose this setup. If we want active high, we will choose this setup. If we want active high, meaning if you push the button, you will have logic 1 inside. Now, what if you want what about the lids? Usually we choose this one because if you have a logic 1 here, the lid will be, or if you have a logic 1, the lid will be on. If it is 0, then the lid will be off. It's very easy to understand. Also, it's easy for our application. So we usually use this setup, which is the current source. Now let's have a simple example. After introducing the symbol boards, the switches, and the lids, let's see a very simple example and try to work things out. And then we will go to more definitions. This simple example says that you want to use a PIC24 to toggle a lid every 200 milliseconds. So every 200 milliseconds, you want to toggle a lid. And you are giving this information that the frequency of oscillation, and remember the talk that we had before about the frequency of oscillation. The frequency of oscillation here is 2 megahertz. Now, when you use a microcontroller to work on any application, you must perform two main tasks. The first one, interfacing the microcontroller, which is the hardware thing to do. And the second one is programming the microcontroller, which is the software thing to do. So let's start with the interfacing, and then after that, after doing the interface based on our needs for this simple example, we will program it. Now, to understand the interfacing and also make it ready for programming, we need to talk about using kits for the BIC24 to make it easy to load the program from your laptop or your computer to the micro controller. So we have many options. We have BIC2, BIC3. We have also BIC4, and I believe they are working on BIC5 right now. And we also have the Snap board. This simple Snap board, I maximize it here. This is what we are going to use in our class and also our lab. As you can see, there are so many things inside. We are not going through it. We just want to use this Snap to be able to program our microcontroller. You can see that there are two ports here. You have the USB connector, and you have an 8-pin SIL programming connector. The USB, you obviously know that. The USB will be connected to your computer, and this these connectors, starting from 1 to 8, will be connected to your BIC24 or your microcontroller. So as you can see here, this is the Snap. This is the cable that you are going to use or to connect to your computer. And on your computer, you will use MPLAB IDE with the appropriate compiler. For our compiler or for our BIC24, we said that we will choose 16-bit compiler. And once you're done with the program, you will upload it into the microcontroller through the Snap to the microcontroller through the connectors here. The connectors, as you can see, there are 8. The important ones are 1, 2, 3, 4, and 5. 1 is the master clear, and you can see that it's active low by having this mark. Also, you have VDD and VSS for 2 and 3. Once you connect these 3, it's ready to be programmed. 4 and 5 will be connected to the appropriate pins for the programming. One for them will be for the data, and the other will be for the clock. Now, for our example, it's very simple. We just want to toggle a LED every some time, which is 200 milliseconds. So we are just connecting a LED to the BIC24. So let's have the BIC24. This is one way of showing the BIC24. And here we choose we apply the minimum connection that we just said. We have a switch for the reset. And we have the AVDD, and the VDD is connected to the VDD, and the others are connected to the ground. The VDD cap and VDD core is connected to a capacitance with 200 or 22 micro farad. Here we chose only one GPIOs, one of the GPIOs, which is RA1, and we connect it to a LED, and the LED is in series with a resistance. Now, should you make the resistance before the LED or after the LED, doesn't matter much. It's fine. You can connect it this way or the way that I just explained in one of the slides before. So that's the only connection or the additional connection so far above the minimum connections that we talked about. So once you have the minimum connections, you're connected only RA1 for the LED. RA1 here means that I chose port A, and I choose bit number 1 of port A. I know now port A is from bit 0 all the way to bit 4. So I choose only bit 1 of port A to connect it to the LED. Okay. Other than that, now we connect this to the Snap hardware. Now the Snap, you will before using the snap, you might use your laptop or your PC. You do your program and make sure that it's correct, the one that we will explain in the next slide. Once you're done with the program, you will feed it to the microcontroller through Snap. You will connect the USB port to your PC or laptop, and then you will connect pin number 4 and pin number 5. One, as we said, that's the BGD and the BGC, the data and the clock. The BGD will be connected to the data, which is the BGED1 in the BIC24, and the BGC for the BGEC1 of the BIC24 microcontroller. Also, we connected pin number 1, which is the reset. We connected directly to the reset, bypassing the switch. In case you want to do the reset using your snap kit. So if you want to do the reset directly, you can. If you want to connect a switch for the reset, you also can do that. So now we have 2 reset options. Now, how to write the program? We said that we will use a C language to write our program, and we will use the MBLab IDE. Now, the program that we are going to write to do the job that we described, which is toggling the lid every 200 milliseconds, is this one. We have the main method, and we have a delay function. In the main method, we said in the first statement, trace A is equal to 0. And this statement will set port A as an output, the whole board with all its pins, meaning A0, A1, A2, A3, A4. The 5 bits all are set to be output using this statement. Trace A is actually a tri-state buffer for board A, and we make it 0 to set it as an output. Lat A is equal to 0. This will create the output port A. So you will have the value from RA0 all the way to RA4, 0, 0, 0, 0, and 0. Lat A is standing for the latest value in the internal flip-flop or the internal latch is equal to 0. So the first statement, you can choose to make the board output or input. If you make it equal to 0, that's an output. If it is 1, then it's an input. Obviously, we'll make it output because it's connected to a LED. The value at the beginning, we randomly choose it to be off, meaning that the LED at the beginning will be off. It's not going to emit light. And then we have a while loop. We delay for some times, and then we toggle the latest value of port A. So we toggle the value at the port, which is in turns connected to the LED. So it will also toggle the LED. So it will be on and off and on and off. We must have a delay. Otherwise, you cannot notice the toggling by your naked eye. So you must have an appropriate delay to be able to see the difference in the LED when it goes on and off. Now we chose, or we give you this in the requirement, that we need the delay to be 200 milliseconds. So this delay function is detailed here. It's a very simple method. If you know that the delay is equal to the instruction count per iteration for any loop, we chose to write the loop using for. So we have a for loop, and we need to loop inside this for sometimes for some iterations, and the collective time for every iteration we want it to be 200 milliseconds. So to calculate this delay, the delay will be equal to the instruction count per iteration multiplied by the cycle per instructions multiplied by the number of iteration divided by the frequency. So if you know how many instructions you have, And also that's the instruction within the for loop. So if you know the instruction count and you know how much or how many cycles you need for every instruction, and also you know the frequency, and it was given 2 megahertz, and the delay that we want is 200 milliseconds. So this, and this are known. The only one that is missing is the number of iteration. And that's what we want to find. The iteration will be equal to the delay times the frequency divided by the instruction count per instruction times the CPI. So plug in the values. The delay is 200 milliseconds. The frequency is 2 mega. And the instruction count per iteration. If you go here through the for loop, the for is from an index I, from 0 to a number that we want to find. And you increment it every time. So you will go through 3 instructions: the comparison, the no operation instruction, and the increment. Comparison, NOP, increment, and so on. So for every iteration, we have 3 instructions. So we have 3 instructions here. And we know that the CPI is equal to 2 because we need 2 clock cycles for every instructions. And we explained this before. If you calculate this, it's going to be, as you can see, 66,666. So this value will be the number of iteration. And this way we will have this amount of delay. So we will delay 200 milliseconds, and then we will toggle. At this point, this is very simple example. We just programmed one port using the 2 statements here, and we also used the things that we explained in the C language lecture, which is the negation or the inversion or toggling the value. This is a bitwise operation, as you can see. And this way we were able to program a port. Now, how many ports we have? We know that they are A and B in our microcontroller. How to program them, no matter what's the application, we need to go into a little bit of details. So the general purpose I/O, they are the simplest type of I/O via the BIC24 microcontroller external pins, and they are also called parallel I/O. Or the PIO ports, meaning that you can push the values in port B, 16 values at one click. Similarly, for A, you can push 5 values in parallel in one single click. In any microcontroller or in any BIC24, you could have many ports, A, B, C, D, and maybe more. But for our specific one, we have only A and B. So each port, usually there are 16 bits or less. In our BIC24, as we've explained, port B is 16 bits, port A is only 5 bits. Now, this is the name of our BIC24. It's BIC24 HG32GP202. It has 28 pins, as we've said. Port A bits goes from RA0 all the way to RA4. And port B has 16 from RB0 to RB50. Each one of them, they are usually referred to as port X. So you could say port A0 or A3 or B15, things like this. Each pin of these ports can be either programmed as either input or out using the TRIS or a tri-state register. We have TRIS X. X specifically, we use X when we want to say TRIS A or TRIS B. So we have TRIS X, and you can say that they are equal to 0 or 1. And you can see the similarity here. If it is 0, then it is output. It's the letter O and the 0 have the same writing. It's a circle. and the input is equal to 1. You can see it's just the resemblance. You can see it between the 1 and the I, just to remember them right away. So whenever you have a trace A is equal to 0, means that I'm trying to program the GPIOs and I choose port A and I want to make them. If I choose equal to 0, then I want to make A output. If it is 1, then I want to make it input. For the LAD X, meaning LAD A or LAD B, same thing for the port X. But they are registered which holds the latest value written inside the internal flip-flop of the specific port that you choose, whether A or B. So LAD for the latest value and port for the value at the pin. And we will see the difference between both of them soon. Both of them, if you make them equal to 0, it means that the value on that port or the latest value is equal to 0. If you make it 1, then the value is equal to 1. It's very important to distinguish between the trace at one hand and the latest and the port on the other hand. To see all the details, they are written in the data sheet in detailed, and this is an organized way of looking at it. We have trace A and trace B. You have trace A, we have the 5 bits of port A, and you can set every individual bits by itself. So you can choose to make this input or output based on your choice, or you can set up the whole register, meaning I'm setting up the whole port. For trace B, same thing. The only difference here is that port B is starting from 0 all the way to bit 50. So trace X is a tri-state register bit. If you choose to make the value equal to 1, then that means that that specific pin is an input. If you make it 0, then that pin is an output. Now, trace A and trace B, they are special function registers. And for these tables, we will see them in many tables throughout the class. And you can see for above every one of them, we have specific options written down here. If it is R, then this is a readable bit. W means that it's a writable bit. If it is U, like these three, then it's an unimplemented bit. If you have the hyphen N, this number is the default value. So the default values for all of them is 0, meaning that the default value for all of the ports, we set them as outputs by default. If the value is equal to 1, it means it's set. If it is 0, then it means it's clear. If it is X, then it is unknown, or we don't care about the value. Okay, let's go to the latest value. So here we have the same thing for A and B. You can see the difference. We say late A 0, A1, 2, and so on. We have late or lat B 0, B1, B2, and so on, all the way to 15. Now here in the latest value, or lat X, the latest value in the internal flip-flop, if the value is, if it is 1, then the latest value is 1. If it is 0, then the latest value is 0. When we say latest, it means that the latest known value. So if you want the most updated value, it's going to be in the internal flip-flop. Same thing for the port A. The naming is different only, but now these are the pin value. The pin value. If it is 1, then the value is 1. If it is 0, then the value is 0. Now, we will also explain this more, the difference between the latest value and the port. in the coming few slides. But let's practice how to set them, or set port A and port B as input and output through some examples. So if you were asked to set the upper 8 bits, only the upper 8 bits of port B to be outputs, and the lower 8 bits to be inputs. This way, we choose the lowest byte, or the least significant byte, to be FF, meaning that the values, all the 8 values here are equal to 1, so they are inputs. And that's what we want. And we have 0, 0, so we want the most significant byte to be outputs. So we put 0 and 0. Now, what if I want a specific bit, or a specific bit in a certain board? So if I want to drive RB15 and RB13 high, and I want all the others to be low, I can do it. You can see it here using bits. I make them all 0 except the bit position 13 and the bit position 15. And that in hexadecimal is A. So I can write it down this way. I say port B is equal to 0x 0, 0, 0, and A. Let's see these while loops. What does they mean? So here we have while port B and be careful, this is bitwise and 0x1000 is equal to 0. This means, and be careful of this, we have a semicolon here. So the while, after you have the condition, there is nothing in the body. This means that you will be stuck in this while loop as long as the condition is true. So for this one, the test will return true while RB0 is equal to 0. So the loop, you will get out of this loop, or you will exit this loop only when RB0 is equal to 1. Why we specify RB0? Because we have 1 here in hexadecimal, and we know in binary it will be 1, 0, 0, 0, and this one for RB0. So if RB0 is equal to 0, you will be stuck inside the while loop. If it is 1, you will get out of this loop. For the other one, we choose RB3. So we change the appropriate value. We know that the first hexadecimal digit here is 8. So it's 0, 0, 0, 1. I know that this is the RB0. This is RB1, RB2, and that one is RB3. So the point of interest here is RB3. If it is 1 equal to 1, then you are stuck inside the loop. If it is 0, then you get out of the loop. More example to get familiar with dealing with the ports, port A or B. Here we choose B. Similarly, we can do the same for A. It's also important to differentiate between the trace and the port. The trace for setting or configuring the bin. Is it input or output? And the port, or the latest, or we call them port and lat, these are only for the values, the specific value. So let's continue. Now, you can actually specify a bit within a port. So you can specify them by rename or calling them by name in the MP lab using the C language. If you see underscore, understand that this is bits. We are talking about a bit, a single bit, and sometimes it's small group of bits. So if you have underscore RA0, we know that we are dealing with port A, bit 0. RB1, port B, bit 1. RB0, port B, bit 0, and so on. And this goes nicely with what we've described here. So if you choose for example, the latest, this will be A0. So you can take the value here using, or let's have the port for the port one. You can, if you choose A0, if you call underscore R A0, it means this value. It means this value, and so on. So you can call a specific bit, or you can call the whole thing, the whole board, with all the 5 bits of A, or with all the 16 bits of P. That example that we've explained was for the whole board, and this one that we will explain now is for a single bit. So here in the while loop, we say underscore RB2 equal 0. So you will be stuck within the loop as long as port B at bit 2, that bin in the microcontroller, as long as it's equal to 0, you will be stuck inside the while. Otherwise, you will exit the while. And that's another example for another bit, port B, bit 3. Okay. You can also rewrite this one using this way, and you can rewrite this one using this one. Now, we talked about the different boards, whether they are output or input, how to program them, how to configure them as input and output, and how to set their value, whether 0 or 1. Since we talked about inputs and output, for inputs, make sure you always have a resistance. Have a resistance between the VDD and the ground. When the switch is pressed here, the RB3, you would read it as 0. So if the switch is pressed, you will have the ground connected here, so you'll read it as 0. Otherwise, if it is in the release state, it will be 1, as I explained before. And that's fine. Now, if you forgot to have the pull-up resistor, and you have a switch and you connect it directly as an input. Now, if the pull-up not present, the input would float. So if the switch is in the release state, we have no idea what's the input. It could be anything. It could be something between the 0 and 1. And this also might be affected by noise easily. So never do this. Always have a switch connected with a resistance to the pull-up. That is, if you chose to use an external resistance. There is another choice that you can make, and we will explain it soon, where you use an internal resistance. So now let's see what's behind the tri-state buffer. Just know that you could have a buffer that connect A to Y. So this output would be A based on an enable, an output enable. So at this point, it's an active low. So if you have the value here 0, the A will be connected to the Y, or the A will be seen at the output. If it is 1, then A is not connected to Y. You have open circuit, and Y will be floating or high impedance. Now, from this discussion, the output, it could be 0 or 1 based on the value of A. If the A is 0, it will be passed to be 0. And if it is 1, it will be passed to be 1 if the output enable is active or asserted. Or at this point, it's actually active low. So if the value here is 0, you will pass at the output 0 or if it is 1, then the value will be high impedance because there is no connection between the A and the Y. So basically you can say that you have a buffer, but after the buffer you have a switch controlled by the output enable. Now I'm explaining this to see the relation between the tri-state buffer that we know it in hardware and the tris value or the tris statement for port A and port B that we are using in the C code to program the microcontroller or configure their I/O to be input or output. Now, let's say you have two big 24s, two microcontrollers, and you are choosing one pin here and another pin here, and you are connect them together by a wire. Inside the microcontroller, you will have different flip-flops, as you can see here. We have 3 flip-flops. One flip-flop, one critical flip-flop is the tris flip-flop. It has the value that you program in the code. You say tris A is equal to 0 or 1. It will be stored in here. So if you make the value of this particular big 24 equal to 0, this 0 will activate this link. So it's going to work. Remember, when we put the tris equal to 0, it means that we having or we are configuring the board at this big 24 to be output. So this way we make it output. Now for the other one, it must be input. Otherwise we will have a fight. So it must be an input. To configure this as an input, I will make the value here equal to 1. So if I make this value equal to 1, since this is active low, there is no connection here, and the value will pass inside the big 24. Now here we configure this pin to output, and we configure this pin to be an input. Now what about the value? What about the value? Now the value at this port here, this is actually the latest value, and we will see it soon. This is the latest value that is saved here. The latest value is moved from the output, and it's stored in the flip-flop here. It will be stored here. And you can see that there is so many other buffers with different functionality. For this buffer, it's obvious that it's connected to a read port. So if you want to read the value, this buffer will be connected or it will be active, and it will connect this line to this line. And this way, you will read the value all the way to the bus inside. Now, how do we get the value that we send to the other microcontroller? We get it actually from the data bus, and it was automatically stored in this flip-flop. And once you have a connection here, by enabling its stress and to make it an output, it will be connected all the way to the output. Now, can we have the other direction? This is this direction. Can we have the other direction? Obviously, yes. You only need to change the configuration in the tris flip-flop. This one we will make it 0, and this one you will make it 1. And this is the relation between the C statement and the hardware. We draw it here in a simple way, and you can see from this discussion that this could be actually bidirectional and half duplex communication. Bidirectional, I can make it this direction or this direction, and it's half duplex, meaning at a certain cycle, it could be moving from one to the other microcontroller, or vice versa, from this to this board. In communication later, we'll see and discuss the differences between the simplex communication, half duplex communication, and the full duplex communication later. But for now, we see that it could be bidirectional, and it could be also half duplex. A quick explanation that for the simplex, it's only one direction. So within a cycle, you have only one direction from one place to another place. That's the simplex. The half duplex could be any direction, but at a single cycle, you need to pick one of the directions. That's the half duplex. The full duplex, you can have both direction at one cycle. So you can send and receive at the same clock cycle. That's the full duplex. So if you have, for example, one simple application for the half duplex, this is what we use by using our phones. If you talk to somebody, usually you talk and he listen, or it's the other way around. He talks and you listen. So it's a send or receive. The full duplex means that both of you talk at the same time, and also you can listen. But that's for another subject. And now we know how to deal with the trace. Let's look deeply what's inside or what's behind every GPIO pin. So if we pick one of the pins, that's a pin here. It could be port A0, 1, 2, 3, 4, or 5, or any of port B from 0 all the way to 50. It could be any one of these ports. You can see some of what we discussed in the past slide. You have this tri-state buffer. You also have this latch for the trace, and you have only a single of this latch, or actually it's a flip-flop. This flip-flop for the trace, and this flip-flop for both the latest and the port. And now we can see the difference. So that's what we have. We also have other buffers. For example, these two buffers for reading. It's up to you. Do you want to read the latest value, or you want to read the port value at the pin? Also, you have this buffer if you want to read the trace value. And usually you read the trace value for testing purposes. Other than that, we have the connections that you have here. And we have many connections because you can see that every GPIO, it's multiplexed with other functionalities, with other purposes, as we mentioned in the beginning. So to choose which one you want, you should have multiplexers. As you can see here, the controller for these multiplexers is the peripheral module enable. So if you want the functionality to be GPIO, you should choose the value here to make it 0. So if it's 0, you will choose this and this. If you want the other peripherals, then you will choose one, and it will give you the peripheral output enable based on whatever functionality was multiplexed with it. And the other feedback here will be used in the peripheral module. Our focus here is for the GPIO. So we want to understand the trace, the latest, the port, and also what's happening here. So let's look at this. But before we go deeply, you can notice that we have this right after the bin. In the back of the bin, we have the ch8 trigger input buffer. So what does that do? We need to explain it, so we want to get it out of the way. You know that this buffer is called ch8 trigger input buffer. Each PIO or parallel input output input has this buffer, and its functionality the function that it does is wave shaping circuit. And basically, it transforms slowly rising or falling input transition into sharp rising and falling transition to have as clean as clean of any wave to make it as square as possible. So instead of having something like this for input and output, let me draw it nicely. Instead of having something like this is for the rising and this is for the falling. You will have it sharper, so it will be something like that. Trying to be as precise as possible. So it's a kind of sharp. There is a slope in the rising and the falling, but it's sharper than something like. So that's the idea behind it. And you can see it here. This is the, or this figure is plotting the Vn, the input, against the V output. We know that the VDD should be 3.3 volt. And this is if it is low, and this is if it is high. You can see that these 2 points are interesting to us, which is the 80% of the VDD, which is 2.64, and the 20% of the VDD, which is the 0.66 volt. And the Schmidt buffer will work like this. So in case you are rising, you will have sharp rising as soon as possible. The moment when you are rising, you will accept it as here. You are already in the high voltage. You can accept that. That's the minimum of the high that you could accept, that point. And in case you are falling, you will choose the other curve. So as long, or this is the maximum value that you still consider it as a logic 0, and this way you make it sharp. Now let's go back to our discussion. We will go through it step by step, only for the trace here. This is in case you want to make this pin output, or in case you are trying to write. You want to write. So at this point, you will choose this pin to make it 0. So you choose this input and this input. This input is actually the output of the trace latch or the trace flip-flop. So you should program the trace as 0. So you will write it down in your C code. It will go through the bus, the value will go through the bus, and it will be stored only here and not here. To make sure that the trace is stored here, the moment the value is there, the clock will be activated. So the writing clock of the trace will be activated. So you will have a falling edge here and the value will be stored. So you have 0 here. And we know that since this is 0, the 0 will be connected to this tri-state buffer, and it will enable the connection because it's active low. So this means here that now the value, whatever value of the data that you stored here is going to be getting out all the way to the outside pin. So now you program this pin to make it output, and you write the value out. Depends on the value. If it is 0, it will be 0. If it is 1, then it will be 1. You are outputting 1. Notice that we don't use the Schmidt trigger input here. It doesn't matter to us because this is the value that I just generated, and I'm sure that all the rising values and the falling values, they are as sharp as possible. Only use this if you have an outside value that comes from the outside, then you use it to make sure it is sharp. Now, how to store the value here? Again, same thing. You have the data bus. whenever the value is here and you want to connect it to store it inside, then you assert the right clock, whether it's for the latest or for the port. And now we noticed here that it doesn't matter what's the value in this latch, it will be transported all the way to the pin. This means that when you are writing, when you are configuring your bin as an output and you are writing out, the latest or the port values, it doesn't matter. They are equal to each other. So they will be the same. Now let's go to the read. Now here we will distinguish between the port and the latest, or the lat. So first we will read the port and see what's going on with that. Now, I think the idea here is a little bit clear. We choose here 0. So we will have the value of the trace. Now the value here is 1. So this path is not connected. So it's not configured as an output. It's actually configured as an input. So it will receive an input from the outside through the ch8 trigger. It will make sure that it's sharp. And then it goes all the way here. And it will be saved inside the data latch. Now, when you read and you use port X, whatever the port is, A or B, if you want the port, then you should activate the read port buffer. Only this one. You activate this one. And this way, whatever value in the bin, notice now when we say port, we mean the value at the pin. It will be read and it will be saved inside the flip. So a reading port X reads the actual bin. Now, reading the latest or the lat value, what you are doing here, same thing for the trace, but now you don't read the bin. You don't read the bin. You activate the other buffer. You want to read the latest value. Whatever value you are having in the latch, you will feed it back again here. So you want to read the latest value. And from this discussion, we know that there is a difference between the latest or the lat A and port A, or lat B and port B. They are different. And this is what we said at the beginning. I didn't want to jump and say it at the beginning here, but writing latx is the same as writing port X. Both writes go to the latch, but reading is different. Reading latx, read the latest value written. Reading port X, read the actual bin directly. And that's the main difference. Okay. And again, we say this, writing latx is the same as writing port X, but reading is different. Reading latch X reads the last value that was written in the internal flip-flop, while reading the port reads the actual bin value. Now, look at this example. This is very quick. Let's say that you have RB3 and it's connected to a ground. But you configure RB3 as an open drain output. Anyway, for now, you configure it as an output. So this is an output value. That it will output something from the big 24 outside. Then you want to write 1 to it. You want to write 1 to it. Now, the physical bin is tied to the ground. So in case you are reading, if you read underscore RB3, it will give you 0 because the bin value is connected to the ground. But if you read lat B3, it will return 1. And the reason is because when you configure it, you actually write 1 in the latch. So now they are different. Luckily, usually what we do, if you configure RB3 as an output, you don't connect it to ground directly, you actually put a lid there so you can see what is going on, or connect it to some other functionality, and it can show you some results. Now again, here's some other differences. If you choose underscore late or lat b, and then you program another one, two different statements, one for port 0, one for the bit 0 of port B, and one for bit 1 of port B. It doesn't matter what's the value. Anyway, you saved something. Here we say it's equal to 1. What you do when you compile the code, it will generate certain instruction. This instruction is the bit set and the bit clear. It depends on the statement that you use. Here it will be only the bit set. So you set a value and you set another value here. The bit set and the bit clear instruction perform what we call read, modify, write. And at this point here, when you use the latest, it will be performed as expected. So you read the latest value of port B, you modify its content, and then you write it back if you want. And this will be fine. But if you use the port, which is the bin directly, if you use the bin, now it will be translated this way. You see the differences here, the latest, and this is the port. Now again, it's a read, modify, write. Again, it's also here. You read port B, you modify its content, and then you write port B again. Now the problem here, because of it's an external bin, so it has different loads. For you have no idea what's this load, maybe it's too much. So because of the bin loading and the fast internal clock speed, the internal microcontroller, it will be much faster than what you have, or the value that you have at the bin. So the changes in the internal flip-flops is very quick compared to a change in the external bin. So this second B set, which is this one, if you use port B, it could fail. And that's why we better use the latest value, the lat X, when you are writing to a bin. So these are actually the difference. I wanted to have this talk later. When you have the codes, we will try to best of our ability to abide by these. However, when you write a code, you usually don't put more attention to the latest value or the port. And when you run the system, usually both of them will be fine. And that's what I'm saying here. If you use latest, the latest value or the port value, both of them will be accepted in this class. But it's very well, or it's very good to know the differences. Now, for the internal weak pull-ups. Now, we know the trace, we know the values. The trace configure input or output. The values, maybe they are 0, maybe they are 1. That's it. You think that this is all about the GPIOs. No, you have more than that. There are things or some features that they are advantageous to you that you should know about, and some of them you must configure. So we will go through them. I think there are only 3. So we have first the internal weak pull-up. There are 2 types of pull-up, the external pull-ups and the internal pull-ups. The external pull-ups, you can have this or look back when you have the external pull-up from slide 5. When we have the switch and we have a resistance in the pull-up. So I told you that you must have this resistance in the pull-up, otherwise you'll have problems. You might have a don't care value. So you can choose here. You could have the external pull-ups, so you must connect the transistor yourself. Sorry, you must connect the resistor yourself, or you could make use of this choice. which is the internal pull-ups. They are an external bin with the CNY bin, or the change notification bin. It has a weak internal pull-up that could be enabled or disabled. Meaning, instead of having an external pull-up connected to a VDD, what you could do is have a switch, this switch, and enable the weak pull-up. This way, you will have VDD and the resistance that is internal connected to the switch. So you don't have to have the external pull-up. And this way, you get rid of this situation. So if you connect the switch directly, you must enable the pull-up. The worst thing that you could do is having a switch connected this way without an external pull-up, and also you disable the internal pull-up. So you don't have a resistance after the pin or before the pin. If you don't have the resistance here or there, that's going to be troubling to you. You might have a don't care. But if you don't want to have the trouble to connect the resistance yourself externally, you could activate the resistance inside, which is the internal weak pull. Now, how to do that? If you choose, for example, a port B and bit 15, you can see alongside it, there's many multiplexed functionality, and one of them is the CN. It's called change notification, and currently the change notification, I will explain it here, but it's not going to serve anything for us right now. The change notification, it's actually notifying you if there is a change in the bin, and this change could be from 0 to 1 or from 1 to 0. This is what we mean by change notification. However, the benefit of the change notification interrupt is going to be discussed later when we talk about the interrupt module. For now, we want to set up the pull-up bin, and we set it up by using this change notification bin. Now we work with RB15, for example, then we need to work with change notification 11. So to enable that, we would say change notification 11 pull-up enable is equal to 1. Is equal to 1. If you that's if you want to enable it. If you want to disable it, you will make it 0. And we will see many examples through the this lecture and other lectures. Also remember to use the underscore. You must have underscore since this is a single bit. If you use, for example, RB14, then the associated change notification or the associative internal pull-up is the CN12. Now, the hardware behind this is not required for you, but it's good to understand it. It's just a resistance, and the resistance that is connected, it's a weak PMOS. It's a weak PMOS that is activated by this statement, a change notification Y, pull-up enable, whatever you choose here, 11 or 12, or any other change notifications. If you make it 1, it means that you are enabling that, and you make this value equal to, or you make the internal resistance active. So when we connect switch, usually when we have a switch, which is an input, we usually make it enabled. We make it enabled. Okay. That's for the weak pull-ups, and this is the conclusion. If you have a switch, it's an input, configure the trace, meaning that the trace should be equal to 1. And then following that, configure its appropriate change notification and make it enable. Next, we have the configuration of any board to make it either digital or analog. So if you choose RB15 again, you must specify, do you want it in analog or digital pin? For now, we will use digital. Later, when we talk about the analog to digital converter, which is the ADC, we will configure this bin to be an analog. Now, how to make sure it is digital? If you want this to be an input, for example, you would say underscore tris port 15 is equal to 1. Now it's an input. Remember, input I, so you have the tris equal to 1. Now, if you want it to be digital, you need to disable the analog function. And to disable the analog function, we would say underscore BCFG 9 equal to 1. How did we get the 9? We go here, and now we look for the analog. Now, the analog 9, meaning we make underscore BCFG 9 equal to 1. And this could be deceiving to you. Usually, when you have 1, it means inactive. Nope. Here, when we say it's equal to 1, it means that you are disabling the analog and you are enabling the digital. So you get the number from the analog AN9 in the pin diagram. Also, it's good to know that when we say underscore BCFG 9, we mean underscore board configuration of this AN9 is equal to 1, meaning that we are disabling the analog. Just as a rule of thumb, so you remember, we will always disable the analog, meaning the BCFG is always equal to 1. Only at that chapter or at that lecture, when we talk about the analog to digital converter, we will enable it and we make it 0 at that time. But from now on, you will have it equal to 1. You must make it equal to 1 to RB15 to make RB15 works. Now, same thing if you want an output. If you want tris P15 to make it output, you would say that the tris is equal to 0, and you also need to disable the analog. Now, if you go through the bins, some of them you will see AN and a number after that. It means that this bin could be configured as digital or analog. Some other bins, they don't have the AN. Some of them, they don't have AN. So you can see some, for example, RP, I believe RA, probably one of the RAs, if I remember correctly, RA4, I don't think it has an analog, and we will see examples. So as we mentioned, bins with shared analog to digital functions have a maximum input voltage of VDD plus 0.3 volts, so it's 3.6 volts. If it is digital, it's 3.3 or 3 up to 3.6. Usually we just say 3.3. Bins with no analog functions, so they are only digital, they could be up to 5 or 5.6 volts as a maximum. This is handy for receiving signals from 5-volt parts. If you have other systems or subsystems that's giving you 5 volts. Now, most PIO bins can only source or sink a maximum of 4 milliampere. You may damage the output pins if you didn't connect the appropriate resistance as we speak before. So be aware of this. That's the first feature that we talked about, the pull-up. And the second is the BCFG, or configuration of the bin, digital or analog. The third is the open drain output. And this is associated only with the outputs. Each PIO pin can be configured as an open drain output, which means that the pull-up resistor is disabled. the pull-up transistor is disabled. So each pin, behind this pin, you have this inverter, a normal CMOS driver, this simple inverter. So you have PMOS and NMOS transistors connected this way. And if the open drain is activated, then the PMOS is disabled or removed. So you can't drive an output here, and you cannot drive it to make it high. And to do this, if you disable it, then you must connect an external pull-up with 5 volt this way. Now, to enable an open drain, you can do this underscore ODC and choose whatever port you want with its bit. So maybe you say underscore ODC port B bit 0, and you make it equal to 1. This way you enable the open drain. If you want to disable it, you will make it 0. You will make it 0. Usually, we want to have our own transistor connected to LEDs or whatever system you have at the output. So you calculate the appropriate transistor and you connect it to make sure that there is no damage to this LED or external subsystem. So if you connect your own transistor outside, then you should disable the open drain. You don't want anything from the inside. And that's what this is what we will use usually when we connect outputs. We will disable the open drain outputs. Okay, in case you want to enable, that's an example, ODC B15. This enables the open drain on RB15. At this point, you have everything. We've talked about the TRIS, the board, the LAT, the ODC, the change notification pull-up enable, and the BCFG. And each one of them, as you can see here, this is their job. We said, we talked about the TRIS and the board and the LAT and all its required details. So we know for each one of them, you can go individually to every bit and program it in the C code, or you can group, you can program the whole board, whether it's A or B. But for the ODC and the change notification pull-up and the BCFG, we've seen if you want to program an individual bin of them. But how about you if you want to program the whole board? So to understand this, we will show the special function register for each one of them. This is for the open drain. It's the easiest one. So you have the open drain for A and for B. For A, as you can see, it goes with the TRIS, the LAT, and also the board. Same thing, just the name is different. ODC A0 all the way to ODC A4. And for the B, from 0 all the way to 50. If it is 1, it's enabled. If it is 0, it is disabled. And we said that we want to make it disabled since we want to put our own transistor because we know our system. This is for port A, ODC A, and this is for port B. If you want to configure the whole port, you would say ODC B. Now, for the pull-up enables, you must go to the bin diagram of the microcontroller. If you want a certain port, if you want a certain bit, you go and check its change notification next to it. If it's there, then if you want to enable, you make the value equal to 1. If you want to disable, then you make the value equal to 0. If you have multiple change notification pull-up enable bins that you want to configure, you could use CNPU1 and CNPU2. If you go to the big 24 bin diagram, you could see that there's change notifications. It's from 0 all the way to 30. And some of them are missing, as you can see here. So the CMPU1, it's from 0 all the way to 7. They are all there. And then 8, 9, and 10 are missing. You have 11, 12, 13, 14, and 15. And you can see them exactly which bin are associated with each one of them. And then you have CMBU2, you have 16, and from 17 all the way to 20, they are missing. There is no change notification bits for them. And then after that, you have 21, 22, 23, and also 24. And there are some missing, as you can see, and only these are available. So you need to make sure that, and you need to make sure that the appropriate one is the one you are choosing by looking at the bin diagram, and we will have an example to explain this point. For the BCFG, you have BCFG 0, 1, 2, 3, 4, and 5. 6 and 7 and 8, they are missing. They are not there. And you have 9, 10, 11, and 12, and the others are missing. Now, to configure all these bits together, you use this special function register, AD1 BCFGL. So it's an analog to digital board configuration for the bits that you want. Let's have an example explaining all of this. Let's say that you are giving a special function register, or you are asked to specify or configure RA0 to RA4 as digital outputs with pull up disabled. If you are asked this, how to configure it? Look at the bin diagram. Now you can see these ports. These are the ports that you are concerned with. This is the GBIOS that you have. This is for A and also for B. And we say that the truss, the LATs, the port, and the open drain, all of them goes with the same number and the port with the GPIOs. So if you want to configure them, you configure them with the same port name and the port bit number. But what about the pull-up enable? The pull-up enable, you get it from the change notifications. So some of them have change notifications. All of them now have change notifications. All the way. Continue the RVs. And all of them have change notifications. But if you look at the CNs, you will see some of them are missing. So you will have CN 0, 1, 2, 3, 4, 5, 6, and 7. Then you will try to find 8. You can't find it. And then you will have 9. You can't find it. 10. You can't find it. And then CN 11, 12, 13, 14. And some of them, you have also 15 and 16. And then some are missing. And then you will have 21, 22, 23, 24. More are missing. You have 27 only. And then some missing, 29 and 30. Not all of them are there. So make sure that the correct one that you want to program, if you use certain board with a certain bit, if you use, for example, this one, RB2, then if you want to activate or enable exchange notification, you choose number 6. And so on. Let's look at the analog. The analog, you have this, analog 0, analog 1, analog 2, analog 3, 4, and 5. And you can see that they are associated with some of the boards. And then, if you look for other, like 6, 7, and 8, you won't find any. If you go here, you will see 9, 10, 11, and 12. This is what you have for analog. Some of the boards bits, they don't have analog. So you cannot configure them as analog. They are only digital. Now, the requirement for this problem, this is like trying to get a full understanding of what's going on with the pins. Now, for this problem, we are interested only in the RA0 all the way to RA4. So we have RA0, 1, 2, 3, and 4. Meaning that I should be interested with the CN, their associated CNs. And similarly, with their analog value. These don't have analog. These three don't have analog. Now, to configure them, I want to configure them as an output. I use their trace. I'm doing the configuration bit by bit. So underscore trace A0 is equal to 0. Similarly for A1, A2, A3, and A4, they are all 0 to make them all outputs. Is that it? I'm done? No. I need to make sure I'm configuring the appropriate analog. So I need to disable any analog if it's associated with if it is associated with the pins that I'm using or the ports that I'm using. So I need to disable this and this because AN0 is associated with RA0 and AN1 is associated with RA1. I put it under it so it's clear to you. So I'm making underscore BCFG0 is equal to 1. I'm disabling the analog here. Underscore BCFG1 is equal to 1. I'm also disabling the analog. This could be deceiving to you, remember. Now, continue. The pull-up enables. We have 2, 3. We have actually 0, 2, 3, 30, 29, and 30. So I'm doing that side by side for each port. For RA0, we have the 2. So the change notification 2 will up enable. For the next one, we have 3. For the next one, we have 30. For the next one, we have 29. And for the last one, we have 0. So this way, we make the pull up enable disabled. We make it disabled. Now, why did we make it disabled? It's now nothing mentioned about the pull up enable. Since this is an output, usually we want to connect it to a LED or a system that we want to work with. And what we want here is we don't want any internal resistance in the pull up to be messing up with our external resistance. So we disable it. We make it equal to 0. The ODC, the open drain, similarly, since we want our own resistance, we also disable it. We make it equal to 0. The pull-up enable, we enable it only if it was an input. We make it equal to 1. So if it's a switch, it's an input, we enable the pull-up enable. And this actually looks nice. If it is an output, which means 0, the pull-up enable and the open drain, all of them also equal to 0. It looks like it. The only one that you should be aware of is the BCFG. Let's continue. Now, the same problem. Before we go here, we go again on the ODC. The ODC actually is matching the port. So if you have A0, it's A0, A1, it's A1, and so on. If it's A4, then it is also A4. So it's matching. You don't have to go to the bin diagram and check what's going on with the microcontroller. Now, for the same example now, we will do the configuration, but now we are using the special function registers as a whole. We are not individually doing the bits. We will do the whole thing. TRIS and the ODC, they are really easy. The things that you need to be aware of is the analog or the BCFGs and the change notification pull-up enables. These you need to be careful about them. So let's see the same thing here for trace A. We have only from port A0 all the way to A4. So for these ones, I want to configure them as an output. So I need to choose the appropriate mask to make them equal to 0. So I'll make sure that the first 4 bits and also the fifth one, 0. And the rest, they will be all ones. You can continue 1, 1, 1, 1, and 1, 1, 1, and 1. So this in hexadecimal is equal to 0. This one is in hexadecimal is equal to E. And now I say trace A is equal to its previous value. I don't know, maybe some other bits was configured. For A, we have the whole thing. But for example, you are using B and you are configuring only part of the port B. So you don't want to mess up the other part. This is why we say trace A is equal to trace A, and then we end with this mask. This mask will zero out these 5 bits, making them outputs, and the rest, it won't be changed. They will retain their old value. They will have the same as the previous value. Similarly, for the ODC, we have the same thing here. Now for the analog, we have AN0, AN1, and that's it. That's what we have in the analog. We have only 0 and 1. So in binary, these 2 bits, I need to make them 1 to disable the analog. And the rest, they will be all zeros. That's a big hexadecimal 0. So we have here 3, and the rest, you have 0 and 0 and 0. So now I have to say that AD1 BCFGL equal to the previous value or this mask. This mask will force only these 2 bits to be 1, and the rest, they won't change from their previous value. Now going to the change notification. The change notification, again, for the RAs, we are interested on only these change notifications. So the first 0, I need to make it equal to 0. This is CN0. CN1 is 1. CN2, I need to make it 0. CN3, I need to make it also 0. That's for the change notification pull up. And the rest will be also zeros. That's a hexadecimal digit. So for the change notification pull up enable, I don't have only a single special function register for change notification. I need 2, and that's explained here. Because it's from 0 all the way to 30. So the first special function register can hold from 0 to 15, and then you can continue from 16 all the way to 31, but 31 is not there, so we have only 30. What we want is we want to disable them. So we make the value is equal to 0. So I put 0 in the point of interest that I have. I put 0 here. 1, I don't have anything, so keep it as 1. And here I put 0 and 0. And the rest, I keep them as before. So I keep them all the way ones, not zeros, ones. So this way, just to match what we have here, the pull up enable is equal to zeros. And others will be 1. So I need to make them 0. And here, I need to make it actually F, F, and F. This value here is 2, and this is F, and this is F, and this is F. Is that it? No, that's only for CN pull-up enable equal to 1, CN pull-up enable 1. It's by mistake here is D000, and that's incorrect. It's supposed to be 2F, F, and F. So I'll explain, I'll fix that now. So the pull-up enable now is fixed. The pull-up enable for CN 0, 2, and 3, they are 0. So we have 0, 1, and then 0 and 0, and the rest we have them as F. This one value or this value in hexadecimal is equal to 2. And for this one, the pull-up enable, change notification pull-up enable 2, I need only a change notification. We are interested in the RAs. Change notification 29 and 30. 0, 2, and 3, we already fixed them, which is this one. Now, for the 30 and 29, they are actually here will be F, 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 and the last four bits, they are bits 28, 29, 30, and 31. So I should have it as 0, 1, sorry, I should have it as 1, 0, 0. This is 29 and this is 30. They are zeros, and 1 for the last one. So I keep it 9. 0x, F, 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 and 9 for the second pull-up enable. So you can see that we need to work on these three, and these are fairly, the TRIS and the ODCs are fairly easy. Now, let's have another example. Write the appropriate macros and methods that configure RB13. This RB13 as a digital input and RB14 as a digital output. This is RB14. So this is input and this is output. We need to know the change notification and the analog too. Also, it says draw the schematic. If the RB13 is connected to a switch, RB14 is connected to a lid, and then write a main method to make sure the big24 recognize pressing a switch or your switch that you connected to the RB13. It's recognize this press by observing the lid. So if there is a press in the switch, the lid should show that there is a press. This way, you know that the big24 responded to the pressing the switch, and then it changes the lid. So we also want to write a method that does that. First, let's write the macros and the methods, the C functions that configure RB3 and RB14. We said that RB14 should be a lid. So we have this macro. We define lid1 to be underscore lat B14. So now we configure lid1 to be lat B14. And now in the code, we always write down lid1 instead of underscore lat B14. This is the macro for the output. And then this is to configure lid1. This is the name of the method, configure lid1. And it's an inline. It doesn't return any value. And you have these four statements. One for the output. We make the TRIS B14 equal to 0 to make it output. The pull-up enable, which is for 12. And this match what we highlighted here. This is change notification 12. And the analog 10. So underscore BCFG 10. The analog, we make it 1 to make sure it's disabled. And the pull-up enable, the out or the open drain that matches the same port and pin is equal to 0. So when we say output, we have a LED, it's an output. It's 0 and 0 and 0. Don't forget that this analog is equal to 1. This way, we configure any LED, any output or connected to a LED, it should be configured this way. Now for a switch. In our case, we say switch 1. We name it switch 1. We have this macro, sharp define, switch 1, underscore RB13. This sample, by the way, sometimes it's called sharp or hashtag. It depends on what you want. So underscore RB3. Whether you are using RB13 as a port value or a lat value, both of them are fine. We could use it this way or that way. So now we have defined this switch. Now we can use this switch 1 instead of this name. And we define 2 more macros for any switch. One for pressing the switch and one for releasing the switch. So these 2 macros, it's for the switch test. It tells you the value. So switch 1 underscore pressed, it means that the switch is equal to 0 or it is pressed. If it is released, then the switch is equal to 1. So this is good for us when we have a test in an if statement or a while statement. We can use check of if the switch 1 pressed or it is released directly using these 2 macros. And then we have the configuration. And in the configuration, we have the trace value equal to 1. And the BCFG, the appropriate BCFG, the analog for RP13 is the 11. And for the change notification is the 13th. So this is for the pull-up enable, it's the 13th, and for the analog, it's 11. And both of them is equal to 1. Notice there is no open drain because open drain output is associated with the output. It's actually from the name, open drain output. The input, even if you put it, it doesn't change anything. Anyway, for the input, they are all 1. So it's very easy to remember. And this way, we configure the LED and the switch. We configure the LED and the switch. Now, all what we need is the interface and the programming. The interfacing and the programming. This is part of the programming, configuring the LED and the switch. The interface would be like this. This is the minimum connection that we spoke about before. We have spoken about this. And here the switch, it's connected to RP3. And also the pull-up enable is activated. So this way, the VDD is not connected directly to the ground. And for the RB14, it's connected to a LED. And after the LED, we have a resistance. And we chose its value, as we explained before. It's fine. You can put it more than 470. You can say 500, or you can see 1 kilo ohm. It's also fine. If you put more resistance, actually, the intensity of the light will be affected, but that's fine. Now, this is the main method. For this one, we say this is the main. Now, we call both methods for configuring the LED and the switch. And then we put the value of the LED equal to 0. And through the while, we say if the switch is pressed, then toggle the LED. Toggling the LED, making the value of the LED equal to the opposite value of itself. This is the way we toggle it. Now, is this a correct code? You might think it's correct, but actually it's not. And the reason is LED 1 will be toggled as long as the switch is pushed. So if there is somebody who pressed the switch and he held the button for a very long time, the LED will be toggled the whole time. It will be on and off and on and off and so on. Is that what we want? We want this simple application to tell us that the switch is recognized and it's shown by toggling the lid. Meaning, if you switch once, the lid will toggle one time. If you switch, if you press the switch one time, the lid will toggle one time. If you switch if you press the switch two times, then the lid toggle two times. If you press 10 times, then the toggling will be 10 times. This way, you see that the Big 24 is actually recognizing your press, and it's showing that recognition by changing the lid value. So for this method to work, or this idea to work, we want to count the number of the switch presses. And to do this, to get away from this guy who will hold the button for a very long time, and if you use this code, it will toggle the lid for as long as you are holding this button, which is wrong. If you press once, it should toggle only once. That's the mentality here. And to do this, you will change the code slightly, as you can see here. You would say, while the switch one is released, nobody pushed the button, you wait for a certain delay, which is 15 milliseconds. So as long as it is released, you will be stuck here in the while loop. Notice the semicolon here. As long as you are releasing the switch, nobody pushed anything, you will be held within this while loop. The moment somebody push, you need to delay for some time. We will talk about this delay now. And then you will go again and be stuck in another while loop as long as you are holding your press. If you keep pressing and you held it for a long time, you will be stuck here in this while loop. Only if you remove your finger, you will be out of this while loop. You will delay 15 milliseconds, and then you can toggle the lid again. So you will be stuck two times. Within this while loop, while one, you will be stuck two times. One time, as long as you are releasing the switch, you will be stuck here. And one time, as long as you are pressing the switch. And this way, you made sure if you press once, the toggle will happen only one time. Now, to understand this better, we will always say press and release. From now on, we won't say that the switch is pressed. No, we would say that the switch is pressed and released. And what we have explained is written down here. Now, what's with the 15 millisecond delay? This is called a debouncing delay. To understand this, let's look at this example. There is a mechanical property of the switch. Since you are pressing the switch by your finger, it's mechanical. So there will be, or if you put it in an oscilloscope, you can see this fluctuation. This fluctuation is, as you can see, it's bouncing like you are dropping a ball and it's bouncing up and down and up and down. Why we have the switch bouncing? It's when a switch is released, it goes high for T1. So now you were pressing, it was 0. And then when you release it, it becomes high for this T1. And then it generates a fluctuation, the bouncing effect, for T2 seconds. It's like when you are having a ruler against the table, and you are holding your left hand with the edge of the ruler, and the rest of the ruler is in the air, and you are pressing it with your right hand and then taking out. There will be fluctuation for the rulers for sometimes. It won't be stable right away the moment you leave it. It's the same mentality here if you have a mechanical switch. So once you release and becomes high, it goes back again and bounce 0, 1, and 0, 1, 1, and 0, 1, and so on. if not taken into account, it will make a lot of fake press and release effects or events or interrupts. So it will be like here you have a press and then you released, and then you have press, release, press, release, press and release, press and release, press and release for each one of the bouncing. So there should be a way to get rid of this bouncing. There are actually many ways to do it. One of the easiest one in a software method is to have a certain delay that is called the debouncing delay. Okay. Just so you understand the bouncing effect, why do we have this bouncing? It's because the switches are mechanical. They have springs inside them. They have metal contacts. And if you press and release, this spring could connect and disconnect multiple times. So it becomes short and open. That's why. So the debouncing delay gets rid of the whole time. It's estimated to be about 15 to 20 milliseconds. And after that, there is no debouncing or there is no bouncing anymore. And this is why it's called a debouncing delay. It's the amount of time which must be larger than the bouncing time. So the debouncing delay should be more than T2. It should be more than this period of time. There is other methods. One of them is to have a capacitance that can suck in all of this bouncing, but we use the delay. And that's what we had before. Now, there is actually a better way for writing this code. It's using what we described before, the state machine of the system. So it's a switch. You have two states. Either you are waiting for a press or waiting for a release. At the beginning, the switch is released, so you are waiting for a press. As long as you are still releasing the switch, nothing happened, you will be in this state. The moment you press the switch, you will go to the other state, which is waiting for a release. So as long as you are holding this push button and you are pressing that push button, then you will be in the press state. As long as you are pressing, you will be still in this waiting for a release state. And the moment you release your switch, you will go back again to the original state. And now you know that you should toggle the lid. So you toggle the lid if you are waiting for a press and the press happened, and then you were waiting for a release and the release happened. So a press and release happened. Now you can toggle the lid. Otherwise, any other event, you will be stuck in the same state. Now we know how to write a code from a state diagram. And this is what we have here. Again, we define the two states, 0 and 1, and we described this before. We define the state, we call the configuration functions that we just had for lid 1 and switch 1, and then we choose the state to be initial. It should be this one, but even if you choose the other one, it's fine. You should say the state is equal to weight of the wait press. And now you have the while loop. You should have two cases. You are switching the state. Based on the state, you are switching. Two cases. The first case waiting for a press, which is this one, the one that you defined here. And the second one is waiting for the release, the one that you defined here. Now, if the switch is pressed, you are in wait for a press, and the switch is pressed. Now you wait for the debouncing delay and change the state to the other state, which is wait release. Now, if you are releasing the switch, then now you can wait again for the debouncing delay and then change the state to the original state. And now you can toggle. Again, as we explained this before, we can imagine what will happen. Let's say that now nobody touched the switch. You go here in the while loop. Nobody touched the switch. You go here. You are waiting for the press, which is the first initial state. Anybody pressed? No. You break, you go back. Anybody press? No, you break, you go back, and so on. Until somebody press. Let's say somebody press and hold his press. So somebody press, yes. Then what happens is you go to the wait release, which is this one. And now you say, oh, did anybody release? No, he's holding his press. So you break and again, you break and again, you break. Only if he take off his finger. So now he's not holding his press anymore, which means he released the switch. At this point, you go back to the waiting press, and before this, or at that time, you toggle that. That's the way this code works. And this is the same idea that we explained when we had that example at the end of the C programming lecture. You can go back and check it out if you want. At that example, we had 4 states. Here, this is a simple 2-state example, and this is happening always for the switch. We will have this, and we will see it many times in the future. So make sure you understand it. At this point, you have the GPIO covered. The only thing here is an idea about the keypad scanning, and maybe we'll give you some other examples as well. You can have a keypad similar to old phone machines, or you can see them sometimes in the digital locks at outside doors or digital door locks. These bins is organized this way: 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you have star, 0, and hashtag. This is the organization, and you can press any of them. You can see that they are switched. For this example, you can press 8, for example, here. Now, there are connections here. These connections usually, or must be actually, connected to the BIC24, to the microcontroller, so it understands a keypad that is numbered. So what happens is it's connected usually this way. So now you have the keypad with the numbers, each one of them under a switch, and you connect them to one of the boards, whatever you choose. Here we choose RB1, RB2, RB3, RB4, RB5, RB6, and RB7. These are the bits that we choose. So we choose port B, and we choose only bits 1, 2, 3, 4, 5, 6, and 7. These are the one that we choose. The way we connect it, we can change the trace value the way we want. So at this point, we make RB1, 2, and 3 output from the BIC24. If there's connection between any two systems, if it is an output from system 1, it will be an input to system 2. So when we configure trace, always your center of attention should be the BIC24. Is it an output from the BIC24 or input to BIC24? So these are outputs, as you can see. And for these ones, since it is connected this way, it's connected VDD. These are the VDD, and this is the resistance. And now it's connected, and you can see the arrow going like this. And at this point, since there is a connection between the VDD and this point, it's going to be equal to 1. And you need to configure these RBs as we said. So at this point, since there is no key pressed, by the way, these are outputs, and these will be inputs to the BIC24. So you need to configure their trace to be inputs. So at this point, there is no key pressed, and the value of the RBs from 4 to 7, they are 1, 1, 1, 1. So if the BIC24 sees 1, 1, 1, 1 in these ports, he knows, or sorry, the BIC24 knows that nobody pressed anything. So let's say now you are pressing 8. What happened? At this point, we make the value 000 as coming from the big 24 as an output to the keypad. You can see that there is horizontal lines here, and there are vertical lines connected to the switches. So if you press switch 8, what happens is actually you connected this horizontal line to this vertical line. And now it will be affected here. You can see that, oh, now the value is no longer 1111, it's 101. So at this point, the big 24 knows that something is pressed. But does it know at this point that it is 8? Actually, it could be 9 or 7, because both of 9 and 7 connected vertically to the same line. So the big 24 knows it could be 7, 8, or 9. How does it identify that it is 8? It do what we call a keypad scanning. So to do the keypad scanning, it will change the configuration of these RPs. How? This way. First, it will have RB1 only as an output, and these two will make it inputs. So eliminate it from the picture. So I know that I inserted only 0, and then I looked up and I found that RB4 to RB7 is 1, 1, 1, and 1. Now I know for sure it's not 9. It's not the button 9. So what happens next is change again. Now we make this an output, and these two are inputs, so we eliminate them from the picture. And if I looked, now I'm scanning. I scanned the 9, and it's not that. Now I'm scanning the 8, and the 8 gave me the change. So now we know for sure that we pressed 8. Of course, this operation happens quickly because the frequency is very high. So the moment you press something, the big 24 know exactly which button was pressed in a keypad, structured anyway, but in our case, this way. Now let's have one more example. In this example, the problem says, assume one lid 1, and one switch 1, are attached to the processor. On each press and release, and you can notice now, we are using this press and release. We know what does it mean now. On each press and release of the switch, alternate between blinking the lid and switching the lid. So initially we put it one of the cases, and when you press the switch and then release it, then you blink. If you press the switch and then release it, and then you make the lid off. Again, you press and release, it will blink, keeps blinking non-stop. And then if you switch, press and release, then the lid becomes off again. Now, since there is blinking, I need to work out something. Is it going to be forever or a certain period of time? What's going on here? For the blinking, it says that the lid blinking period is 50 milliseconds. Since there is a period, then it will be blinking until I press again. And the blinking period is 50 milliseconds. Now it says right there a main function for this system. And there is an assumption that there is these two methods. Start timer is expired. Start timer, start the time for a certain millisecond. It's already there and it's written. Is expired, does the time expired? One, the time expires. If it's not, then it's going to be, the return value going to be 0. So what we do here, we will draw the state diagram to make the coding easier for us. Since we have only one switch, it's very similar to the one that we just discussed. The only difference is instead of having toggling the lid in the previous example, now we have two cases. alternating between the lid blinking and the off state. And that's why if you look at the code, the previous code and the previous problem, and this code, you will see a lot of similarities. So now you will have the same thing. We know that we define two states. Now we define the state, and we will have a while loop with switching this state, and we'll have two cases. Same thing. We also configure the lid and the switch, same thing. The only thing here is we identify this variable, we add it, which is for blinking. If blink is equal to 0, it's not blinking. If it is equal to 1, then you are blinking. They start with one state, and you chose at the first one to be the blinking state. So it will blink equal to 1, and you start the timer for 50 millisecond. Now, while forever, while 1, if nobody press the switch, then you will be in the blinking state. If there was a press, then you delay 15 milliseconds, the debouncing, and then change the state. If you release, this means that you press and release, you wait, change the state, and now you do the blinking. Now you do the blinking. Now, the blinking here, blink is equal to 1. Now it will be equal to 0 since you toggle that. And you change, or you start the timer again if the blink is equal to 1. So if the blink is equal to 1, you start the timer, which is this function that was given to you. You start the timer of the blinking only if it is equal to 1. How to make the blinking with a certain period becoming on and off? By adding this if statement outside the switch statement. Now it has two conditions. If you are blinking and it is expired, the time is expired, then you toggle the lid and then you start the timer again. So let's say you were blinking. It was at the beginning blinking, meaning that you will have 1 for 50 milliseconds. Is it expired? Yes. Then it becomes 0. Is it expired? Going back again. Is it expired? Yes. It goes again. So it expires only if you pass 50 milliseconds. 50 milliseconds. And so on. This is the importance of this if statement. If you change if you press and release, this will affect the blinking. It will make it 0. So if there is no blinking, then there is no toggle. No toggle, meaning that it will be 0 the whole time. That's this code. And I added this example to know that you don't only work with the cases for actions, you could also work outside the switch for certain conditions. If you have, for example, the output has many types or many configuration. So let's have the one last example. And this problem, it was asked for you to design an interface to provide 24 outputs using the big 24. Remember, port B is 16 outputs and port A is only 5. So the total 16 plus 5 is 21. So that's the maximum that you could have, only 21 inputs or outputs. If you want more than that, in this example, we want 24 outputs. How can we achieve it? Actually, the way is given to you in the question. So design interface to provide 24 output using the big 24 processor with certain frequency, 20 megahertz. And it says use 74HC374, which is the D flip-flop, which is this one. So it says use D flip-flops to expand your outputs. It says assume that there is a setup time of 25 nanoseconds. So this is the setup time. And the whole time is only 5 seconds. and assumes, this assumption is giving you actually more restriction, that only from port B0 all the way to port B10 are available to you. The others are used for other systems or other things or other applications. So these are the only available to you. So how to do that? How to extend the outputs and to make them 24 output from 0 to 10, that's 11 pins. From 11 available GPIOs, how to make 24 outputs. If you think about it, looking at this chip, think about it for a while. You can pause the video and try to figure it out. Here, the D is 8 bits and the Q is 8 bits. So if you use one flip-flop, you will have 8 outputs. How many of these D flip-flops you have to get 24? 8 and 8 and 8. 8 times 3 is 24. So I need 3 of them. If I have 3 of them, I will have 24 outputs. But I need to connect them to the big 24. How to connect them? I'll connect them this way. So this is the big 24. I will use from RB0 to RB7 as the data. It's connected here and here and here. And I'm using 3 D flip-flops. And RB8, 9, and 10 will be connected to the clock to activate whatever D flip-flop that you want. Now, to work with that, we need the appropriate programming. So we will make the correct initialization. The trace B is equal to the trace B ANDed with 0x008F. Remember, we want them in outputs. So the RB0 to RB7, which is the first 8 bits, 0, 0, 0, 0, 0, 0, 0, and 0. This is for the trace. Now, what about the others? We will make them also zeros, which is 8, 9, and 10. And then the rest will be ones. This is why we have 0, 0, 8, and F, 0, 0, 8, and F. Also, you need to do the change notifications and the other bins, but it's not written here. You need to do it the same way that we explained before. Now, the latest value, now we make them output. The latest value of them will be 0x, 0x, FF, 8F. Why 8? The reason is the following. Now, FF, meaning that the first value, now we're talking about the value, not the trace, is going to be 1, 1, 1, 1, 1, 1, 1, 1 for the data. But for RB8, 9, and 10, it will be 0, 0, and 0. Remember, it's connected to the clock, so it will be 0 at the beginning. The value is 0 at the beginning. Now, the method that we are going to use whenever we want to access any of the outputs, which is 1 or 2 or 3, we have output data method. It takes as an argument output 1, 2, and 3, the ones that you want to show up in the outputs here. So you would say lat B is equal to lat B ANDed with 0x00FF. So you want the values to appear, or the data to appear at RB0 to RB7. Whatever, is it output 1 or 2 or 3? So it's always with the same masking. And then you OR it with whatever you want. If you OR it with output 1, meaning that you are interested in this flip-flop, then you give a pulse here. Even this one is not clear. Is it rising edge or a falling edge flip-flop? So you give it both edges, 0, 1, 0. Originally, it was 0. Now, if you give it 1 and then followed by 0, that's 1 and then followed by 0. This means now the data from RB0 to RB7 will be passed to this flip-flop. Now you know that the value in the output 1. And then you move to output 2, and you do the same. Now the only change here is B9. And then also for the third output. So what happens if you have an output that you want to show here, and the outputs are different, could be any values, you feed it first to RB0 and 7, and then you show it to the output 1. And then in the next cycle, you give it here. And then the next cycle, you give it here. It's not actually the next cycle, the next few cycles, because you see that you have multiple statements. That's the way you do it. Now, you also need to make sure of the setup and the hold time. To know this, we can get the amount of time each statement needs to be executed, because we have the frequency of oscillation. So since the frequency of oscillation is 20 megahertz, I know that the FCY is 10 megahertz. If I take the reciprocal, then the time the instruction needs to execute is 100 nanoseconds. So now I need for the flip-flop to work, I need a pulse, the pulse that I just showed. So we have a setup and a hold time. Since the setup is the 100 nanosecond that you see here, and the hold is the 1 nanoseconds, the 100 nanoseconds over there, you know that this is actually a rising edge flip-flop, and the statement that you have here, which is this one, will take 100 nanoseconds, which is more than what you are required to wait for, which is the 25 nanosecond that was given to you. It's here 100 nanosecond. And for the hold, which is this time, also you have the time 1 nano for the other statement. So this will be, the timing will be fine, and you don't have to change any. Let's say if it wasn't in, let's say that it wasn't 25 nanosecond. Let's say if it is 300 nanosecond. How to fix that problem? If there is more time needed, then you could use a delay function or a no operation function with the appropriate number of no operations. And there are many systems that we will work on in the future, and we will introduce how to deal with the no operation later. And this time we talked about the GPIO, the port A, the port B, how to configure their trace, the latest value, or the lat, the port value. Also how to yeah, we looked at the bin diagram, and we know that we talked about a little bit about this Schmidt trigger buffer, and how is the latest value and the port B differ. We talked about the open drain output, the pull-up enable, how to make a bin digital or an analog, and we gave you many examples talking with this. That was the last one of them. This is what we discussed today. This lecture was a little bit long because it's actually the first module. It's very critical and important. You need to understand it very well before we move to any other module. Next lecture, we will talk about the LCD. If you want to connect your output to a small screen that is connected to the microcontroller. So we'll talk about this next